A video to take you to understand how chips are made. It turns out to be so complicated. Let's walk into a semiconductor factory and take a look at exactly how chips are made. This CPU is made on a 300mm silicon wafer, which holds 230 CPU chips, compared to a much smaller chip for a memory stick, which can hold 952 memory stick chips on the same size wafer. Every 25 wafers of the same size are stacked on top of each other and shipped using a container called a front-opening universal box, which also goes by the acronym FOUP. Inside the factory, it is transported on top of the clean room through an intricate overhead transportation system. Once an FOUP reaches the soft landing pad of a given machine, an internal robotic arm transports the wafers through vacuum load locks to different processing chambers, where several more operations are carried out, which require the use of many different tools. Depending on their function, we can categorize them into 6 types: making mask layers, depositing materials, removing materials, modifying materials, cleaning wafers, and inspecting wafers. Let's look at the first category, the production of mask layers on the wafer, using a number of tools, mainly including photoresist spin coater, which is also known as a homogenizer, and then photolithography developer, as well as photoresist strippers. First, look at the screed machine. It will be evenly coated with photosensitive layer on the surface of the wafer. After, it will be sent to the soft baking device, where the wafer is heated. The solvent in the photosensitive layer is gradually evaporated. Next, the wafer is sent to a photolithography machine, where engineers irradiate ultraviolet light onto the wafer through photomask technology. The light passes through the template, which is then continually shrunk, and ultimately forms a nanoscale pattern in a certain area of the wafer. The photoresist is actually weakened wherever the UV light hits the wafer. After this, the wafer goes to the developer and the previously weakened photoresist is washed away. At this point, only nanometer scale pattern templates remain on the wafer surface. Next, the wafer undergoes a second baking process as a way to harden the remaining photosensitive layer. Once the process is complete, the wafer enters the photoresist stripper, where a solvent is used to dissolve and remove the photoresist mask layer. At the bottom of the photolithography machine is a UV light source, above which is a series of lenses to focus the light, which also contains the stencil, or photomask, to be patterned, and finally the wafer carrier, which is below. The UV light passes through the photomask and comes to more lenses in different combinations, eventually reducing the pattern to 4 times its size and printing it on the photoresist on the wafer. During this time, the wafer carrier stays in each place for an extremely short period of time, so that all the chips on the wafer are fully patterned. Next comes the deposition tool, which serves to add or deposit material onto the wafer. But at this point the wafer has already been patterned by the photomask, so at this point the material will be deposited only in the areas not covered by the mask layer. This is well understood, just as we use the model spray paint to create a specific pattern, due to the production of this layer of material variety. So according to the different materials, the deposition tool, and there are many variants. Each variant of the name and acronym are very complex, but the most used materials are only 3 categories: copper or tantalum and other metals, with insulating properties of the oxides, as well as the silicon crystals, each of which uses different physical or chemical principles to deposit them onto the wafer, or chemical principles are used to deposit them onto the wafers. The third category, removing the material, is a step that can be accomplished in 2 ways, starting with etching. Etchers remove materials by reacting caustic chemicals or high-energy plasma with the wafer surface. They are usually used in conjunction with a mask layer so that other areas are not damaged. When the etching is complete, the space created is filled again later with a deposition tool. The second removal method is called CMP, or chemical mechanical planarization, which in layman's terms is the use of chemical slurries to polish and sand the surface of the wafer until the top layer is completely flat. The fourth type of tool, modifying materials, is generally an ion implanter, which uses a photomask as a template and then bombards the uncovered areas of the photomask with phosphorus atoms, boron atoms, or other suitable dopant atoms to form the P and N regions of the transistor itself. In addition, the ion implanter works in a somewhat violent way, bombarding individual atoms directly into the silicon lattice, somewhat like firing a cannon, where the speed is so high that the projectile